Imagine overturning a scientific belief that's been rock solid for 2 decades. That's exactly what astrochemist Julia Santos did, rewriting our understanding of how methanol, a crucial building block for life, forms in the vastness of space. Her groundbreaking discovery has sent ripples through the astrobiology community. But here's where it gets controversial: the implications could change how we search for life beyond Earth. I try to understand chemistry in space, Santos explains, encapsulating her ambitious research goals. When we think about a planet, we envision layers: a core, a mantle, a surface, and an atmosphere. Creating these layers requires a specific combination of atoms. My driving question is, how are these crucial ingredients distributed throughout the universe? Is the chemical makeup around other stars different from our own solar system? Was Earth just incredibly lucky to have the right stuff for life to emerge? Think of it like baking a cake: you need the right ingredients in the right proportions. Santos is figuring out if other planetary cakes out there have the same recipe as ours. Her work focuses on planetary nurseries, the swirling clouds of gas and dust where stars and planets are born. Understanding the chemistry within these nurseries is paramount to understanding how planets, moons, and asteroids ultimately take shape. And this is the part most people miss: it's not just about what elements are present, but how they interact and combine to form more complex molecules. Santos is illuminating the earliest steps in this cosmic dance of creation. How do simple molecules evolve into more complex ones? How are they created and destroyed in space? Are they floating freely as gases, or are they stuck to solid surfaces? Santos asks with palpable enthusiasm. During my PhD, I zoomed in on dust grains and the icy layers that form on them. These ices, believe it or not, provide a surprisingly fertile environment where fascinating chemistry can happen. These dust grains act like tiny cosmic laboratories, providing surfaces for atoms and molecules to meet and react. To tackle these questions, Santos primarily relies on laboratory experiments. We can send probes to comets within our solar system, but venturing further is currently impossible, she states pragmatically. Therefore, we recreate the conditions of interstellar space right here on Earth, using experimental setups that mimic the extremely low temperatures and pressures found in those distant regions. She pursued a multifaceted approach, combining hands-on lab work with theoretical chemical studies and observational data analysis. I need that variety to stay motivated, she admits with a smile. Although, the tangible results from experiments are especially rewarding. During her master's studies, Santos had already demonstrated her research prowess, publishing several peer-reviewed papers, including 2 as the lead author. However, her most significant achievement came during her PhD, her groundbreaking work on methanol formation. I investigated many different chemical reactions, focusing primarily on the formation of methanol. While it's a relatively simple molecule, in the context of space, we consider it complex, she clarifies. Methanol is a key player in astrochemistry, serving as a fundamental building block for a wide range of more complex organic molecules. Consider methanol as the starting material for building more complex space Legos. For 2 decades, the scientific community had accepted a specific mechanism for methanol formation. Until Santos came along and challenged that paradigm. I confirmed that there's another, previously overlooked, mechanism that plays a more significant role, she reveals. We published our findings in 2022, and since then, observational data and theoretical models have consistently supported our results. That's the gold standard in astronomy, empirical evidence, so it was incredibly exciting. This is a major shift in understanding, and it's a testament to the power of rigorous scientific investigation. Santos emphasizes the unique environment at Leiden University as crucial to her success. We are fortunate to have access to specialized facilities and expertise that are rare to find elsewhere. Astrochemistry is inherently multidisciplinary, drawing from geology, engineering, astronomy, and chemistry. Leiden brings all of these fields together, which was incredibly helpful and enriching. The collaborative atmosphere and access to cutting-edge resources clearly fostered her innovative research. However, her journey wasn't without its challenges. My promoter, Harold Linartz, passed away unexpectedly, which was a very difficult time, she shares somberly. And shortly after, we had to relocate the lab. This meant I couldn't conduct experiments for a significant portion of my PhD. Fortunately, Ewine van Dishoek generously welcomed me into her research group, providing invaluable support. Now, Santos is continuing her research at Harvard University with the prestigious 51 Pegasi B Fellowship. But what does this all mean for our search for life? If the way we thought methanol formed was wrong, could our assumptions about the formation of other life-essential molecules also be flawed? And could this new understanding of methanol formation point us towards new places to look for extraterrestrial life? What are your thoughts on how this discovery will impact the field of astrobiology? Do you agree with the implications of her findings? Let us know in the comments below.